Hey everybody, welcome to another assignment video for CS302, and this one is going to be a balanced mobile. So I'm not sure about you guys, but when I was in, I believe, 5th graders, so we had to create this mobile project. And a mobile is, I think we used like a clothing hanger, and you would just sort of take, I think it was like yarn or string, and you would attach it to note cards, and it was mostly to describe I think a plot of a book or something, and then it was just in a nice visual form. So I guess that's where this program, I guess, kind of gets its inspiration from, but I don't think it's really based on that. But I'm gonna call it that. So yes, the mighty mobile. So basically, in this program, it's going to be sort of testing your ability to write code with binary trees. So we can think of a mobile as sort of this device that has two arms. An arm has a length, each arm has a length, and also has a weight attached to it. And also, since it's a binary tree, we can think recursively where we can also have it where an arm, the left and or right arm, can not only be just attached to a weight, but it can also be attached to another smaller mobile. So the whole idea is you want to see if it's balanced, and the idea of balance is that the torque on both sides of the mobile has to be the same. So remember how we compute torque, it's just the weight multiplied by the length of an arm. So if the torque on the left and right side for every single mobile or submobile or tree and subtree is always the same, that means we know we have a balanced mobile. Now, of course, in this video, we'll go over more of the details of this, but that first paragraph in this assignment write-up really just sort of goes into just about that. So let's go ahead and now go over, I guess, the input and output of this program, and then go into the actual class you have to write. Okay, so for the input, you'll be given a set of lines. Each line contains four numbers, or four integers, if you will. So each integer gives you detail of each level of the mobile. So basically here we have a left arm weight, the left arm length. So that's going to be sort of a torque. You can use that to compute the torque of that left arm of your mobile. Then you have the right arm weight and right arm length. Now, in this input, basically if the left arm weight and or the right arm weight contains the number 0, doesn't mean the weight is 0, it just means that there isn't an actual final weight attached to the mobile. It actually contains a submobile, actually, in fact. So basically you're going to have to sort of read this in, and it'll be read in using a pre-order type traversal of a binary tree, and have to also recursively read input from the file as well. But for now, that's going to be our input file. And of course, I'll sort of draw an example of how it's going to get constructed later in this video, but that's how your input will be given. Then the output is going to be just for each input file. You're going to have to sort of output whether the mobile is balanced or not balanced. So you output balanced or not balanced, and of course, code grade will sort of match with these strings. So just make sure, it outputs it all correctly like that. So that's sort of, the input and output. So I'm going to go now into the actual binary tree class you're going to have to write. And of course, I'll sort of draw up an example of how we can visualize an input file, how we can sort of see how the binary tree / mobile would look for this particular input file. So here's going to be your binary tree. I called it mobile type, just I guess because we're going to be representing this mobile type structure. And then each element in this, so each node in this binary tree contains the following fields. This struct is going to maintain each node of your binary tree. So you have these four integer variables. So WL be weight left, DL is distance left, so it's going to be the length of that arm, and WR is going to be weight of that right arm, and then of course DR is going to be the distance of that right arm. Now, of course, if you want to rename these variables to make more sense for you, feel free to rename these. You can call whatever you want, but I just use this, but it's up to you entirely how you want to call these. Just make sure you have sort of the the length and the weight of the left arm, and then the length and the weight of the right arm. And of course, we have to have our left and right pointers that point to our left and right children. So this class is not going to be a templated class, so this will make programming just a little bit easier because, well, I guess there was no way to make a template out of this because it's too specific to this particular instance of the assignment. So it's going to be a little challenging to implement this without a template, or with a template, sorry, so it's going to have to not be templated. So anyway, that's going to be our struct. Now here's going to be our members of our class. Not super bad. A few functions here will be a little bit rough. So of course we have this bin tree node root. So we have our root pointer as always in our class. Of course we have to have a root pointer in order to be able to maintain a binary tree. Then we have this default constructor up top. So this will be our default constructor, and basically it'll just set root to null or null PTR. Nothing too fancy there. Then we have our destructor. So a destructor for a binary tree is going to be a post-order traversal. Actually, literally, it's going to be post-order. You can actually take your post-order code. So right now, actually, I have this function delete tree, so my mistake. So here's going to be, you're going to call this function delete tree in the body of this destructor. And delete tree, when you call this function in the destructor, you're going to pass the root pointer into this function. And then delete tree, this is going to literally be a post-order traversal. You can actually take your post-order code that I gave you in lecture, and all you have to do is, instead of saying cout our data, you would instead say delete r. So this function has the following behavior. If r equals null, return. You call delete tree, pass an r arrow left, then call delete tree, pass r arrow right, and then go ahead and say delete r. If you do that, that will actually deallocate the tree. So you have to deallocate from the bottom up. So you have to first, for every node, you first deallocate the left subtree, then the right, and then delete r. And that will work. So I guess here's a question, you know, do you have like an idea of why do you think that's the way it should be written? So what if I were to have said delete r first and then say delete tree and then pass an r left and then call delete tree, pass an r right? Why would that method not work? So the hint is dangling pointers are a problem in C++. So anyway, there's your destructor. So now the only more challenging functions is going to be this build tree and then the getWeight functions. But we'll worry about that later. So let's first focus on build tree. So this build tree function, this will be called in main. It's a public function, so of course you would in main, after you read in main, you read in your file name, and you open up a file stream successfully, you're going to, of course, you have to allocate or have to declare an object of type mobile type in main, and you're going to have to just call that object.buildTree function and pass in that file stream. And then you're going to have basically this second build tree function, this private one. This gets called within this first build tree function. So in this build tree function, I would just suggest, or it's up to you. Now I don't have this return pointers like I did for the example for binary search trees. So it's going to be a little different logic for how you do this. But of course, actually, you can update this function prototypes a little bit if you want. But I mean, a void function is good enough for this build tree function. You're going to basically, in pre-order traversal fashion, you go into sort of first build. So in this first build tree function, you just create the root node. So you just say root equals new bin tree node, and you just, that first line of your file, that's going to be all of the data for that root node. And then of course, I pass in the root into, so I call this function build tree within that first build tree function, and I simply just pass the root pointer into this function. I pass in that same file stream variable. And then within this build tree function, I just simply allocate a node to r left, and then I recurse on r left if the left weight read from the file contains 0. And then I go ahead and read in a line and assign r right equal to a new node, and I recurse on that right side if the right weight read in was 0. So let's go ahead and sort of draw this out on OneNote, and just to kind of visualize how you could think about that file and how you would have to construct the tree given the file. Alright, so just to recap, I want to make this a bit more clearer. So here is your build tree function you're going to write, and this function, I put some comments here for you. So you want to essentially do the following. So this function is called in main, and you're going to basically just have this function allocate a node to the root. So of course you want to first read a line of the input file. Now of course you can use getLine, but getLine can be a little bit tricky to get it to work in certain instances. So really a simple way is you can, since every line you know for sure contains 4 integers separated by a space between each, if let's say we create a variable, so we'll use in file right there, I could actually have say W, X, Y, and then Z or Z. That will read one line because it's going to read these 4 numbers, and let's say you have to declare 4 integers in your function. This will read in one line from the input file. So definitely a simpler way than actually doing getLine and parsing the file or parsing that line with all that. That's a much nicer, easy workaround in C++. So once you read that one line, you allocate a node to the root, you assign the values, appropriate values to it, then you go ahead and call build tree, you pass in the root and in file, and of course build tree will recursively will build the rest of your tree by reading in one line at a time, and then it will just keep, constructing either a left or right child. The clue to this is that it's going to be a pre-ordered type traversal. So you're going to keep on producing left children until you hit a dead end, or when you have a case where for a certain line, the weight of the left and right are both going to be a non-zero, so it will be an actual value. That means that's a leaf, and of course you return back to the parent and then construct the right child from that point on. So it's a big hint as to how you would do that. Let's go ahead and go into the input file and sort of visualize how the tree would look for this, and how we can also write, how we can think of the function to write the to make sure the tree isn't, or this mobile slash tree is balanced or not. Okay, so here is the first input file we're given in this program, and we have this. So okay, right now we have an empty tree. Now I'm not going to draw this in a binary tree fashion. I'll draw this like in a mobile fashion, but I'll sort of highlight, what each node consists of. So when we first read in our first line, of course, this is going to be the first line we're going to read. That's our first node, our root node right there, like that. So then what's going to happen is, well, we're going to have to do the following. So I'm going to do this in a much more visual type of way. This will be indicating, like, I guess, sort of a junction in our mobile. And I guess I could try, I could try to make this look a little nicer. So we're going to have an arm like this. So it has 2 arms basically. This would look a little better. So in this first line, we have 0 for the left weight, which means that this left side is not going to be a leaf, it's going to be another submobile. But then it has 2 for its length. The right side, so we have first that 0, then that 2. Now this third 0 right there is going to be the weight of the right arm, 0, meaning that, okay, we're going to have a submobile over there. And that last number 4 is going to be the length of that rightmost arm. So this, you can imagine, is going to be just one single node. And this node really looks like a face right there, actually. Looks like a frowny face. But anyway, so this is going to be one node. So we're going to have to store in this node, the left weight is 0, right weight is 0, left distance is 2, right distance is 4. But I'm just sort of drawing it like this, so it sort of makes a bit more sense. Okay, I think you know what picture I just saw right there? I'm sorry, I'm kind of trailing off. That looks like the maybe the Hamburglar? I don't know, something from a McDonald's type of old cartoon character. Okay, I apologize. Back to the actual video at hand. So now that we have this red, so we're doing a pure traversal. So we're going to have to construct this top node's left side next. So the next line of input is going to be that, that left child of our root. So we have 0, 3, 1. So it's going to be another submobile here. So let me go ahead and just sort of, maybe I'll have a line like this, so it looks a little nice. Maybe I'll do this just to denote it's another mobile. And then we're going to have our 2 arms again. Actually, I want to do a shape like this. Okay, we have this basically. So that's not really drawing to scale. That's not as nice. Well, I can try and make it a little bit more even. Okay, good enough. So in this next line, that left weight, that first 0 is our left weight, which means we're not going to have a weight. We're going to have another mobile. And the left arm length will be 3. Then the right one will be also no weight, and the right arm's distance will be 1. So again, we have to keep going left because we're doing a pre-ordered traversal of this. So we first constructed the root node, which was right here. It was our Hamburglar, I suppose. This will be, no, I think I know what this is. This is from Family Guy, that Mr. Hamburger, which that weird episode of Family Guy. It was like based on a Kennedy thing. So anyway, I don't want to go into that though. Anyway, so we have this. And then this is going to be our left child, basically. So if you have a binary tree, these are our 2 children. This is our first node, and then that left is our second child, or left child, basically, as we can visualize. And then, of course, this next sort of element right here is going to have to be the left child of this guy right here. So we see here we have all 1s, which means that now we're going to have a leaf because there's not going to be any more continuation to this mobile. So again, we're going to have to do it like this. So then we're going to have these 2 arms once again. There we are. So this one has a weight of 1. So the left arm has a weight of 1. So I'm going to go ahead and just try to create a circle over here. Okay, that's good enough. So these are both going to have 1, 1, and we have distances like this. So basically here, that's going to be our, so it's not really how the binary tree would look like, but here's how we can visualize it. So again, just to recap, this will be our node. This will be our left child. This will be our left of left child. So we have essentially, you know, this set up so far. So we can see the pre-ordered sort of movement here. If I drew it like this, so it's a bit more easier to visualize, but of course these numbers would be stored in each node's appropriate fields. So now what happens is now we're done with this, we have to return back to the parent, which is going to be this node right there. And since the right side of this was a 0 as well, we have to basically construct the right side of this tree, of this node, sorry. So the right side, we're going to have to read this line. This is that right side of what I just had a second ago, right side of this node right there. So now what's going to happen is I'm going to just construct that by, again, just sort of denoting we have a submobile right there. And we're going to put the left and right arm. Yeah, I'll try to be consistent with the one on the other side as well. And there we are. Okay, so that line, we see a 2 for that leftmost number, which means that that left child will have a weight of 2, then a 4, oops, it's auto complete my mistakes, and then we have 4 for its length. Then we have another, since that third number in this line is not a 0, that means that right sort of side has an actual finalized weight with the length is 2. So there we are. So now we constructed a right side. We have to return back up this tree. Now we have, so we basically, you know, we were essentially here first. Then we went over here. Then we constructed the left side. Then the right side. Now we have to return back. You have now constructed the right side of this root. So we're doing this pre-order sort of fashion essentially here. So in this next line, we're going to have to read, or sorry, to read this next line next. So if we do it in file recursively, it reads the next line basically, but the recursion helps us sort of navigate through a tree correctly. So now we have our, let's say our final sort of submobile. So then here we're going to have again 2 arms. And I'll have an arm right there. So on this last line, that first number 1 means that we're going to have a weight of 1 for this left arm. And then the length will be 6. Then the right arm, we have a 3 right there. So right arm's weight will be 3, and then the length will be 2. So that's how we want to construct this mobile. So basically, I know it's a little bit odd shaped, but I did it like this so it's easier to visualize, but essentially each of these will be its own node. So let me go ahead and just sort of redraw this again. This will be a node. This will be a node of 2 leaf nodes. This will be a node. Then this is a node. This would be the right child. And if a 0 is seen in the input file, that means the left and or right side isn't final. It means it has additional submobiles attached to that left or right arm. So you have to write the code for this, but this is sort of the pattern of how you want to do this. So of course, you construct the left side recursively. Once you hit a leaf, you return back to the parent, and then the right side is constructed. So just that standard pre-order traversal, but more than just C-outing. Sort of, instead of C-outing nodes, we have to do something else. So that was sort of how we construct this tree, given this input file, at least the visual representation of this. So the last part here is going to be how to, determine sort of if the tree is a valid mobile or a valid balanced mobile. Okay, so you're going to call this function validMobile in main. It returns true or false. Obviously, if it returns true, that means the tree was a balanced mobile, was balanced by weight/torque, and a false means it was not valid. So within the function body validMobile, you're going to basically call the function getWeight within this function validMobile. And getWeight returns weights up the tree, which can be used to compare the left and right tree accordingly. So let's go ahead and go back to our image that we drew on the mobile for the input example, and just see kind of how we can verify if this mobile is in fact a valid or it's a balanced mobile. Okay, so we first call the getWeight function inside of valid or validate. No, I think it was valid, whatever, valid or validate mobile. You're going to, of course, pass in the root initially. So what's going to happen is that at the root level, which is right here, we can see that we don't really know the weights of this mobile because this has submobiles attached to it. So we have to, again, do somewhat of a, this would be more of a post-order type logic for this. You have to first compute the weight of these two arms, but we have to compute them recursively because we don't have the weights. You have to determine what the weights are by summing up the weights of previous levels. So what will happen is you first want to go ahead and figure out what's the weight of this first and then this one next. So let's focus on this one. Okay, so you have to recursively, call the function getWeight and pass in r arrow left. So now we're going to have r, the r pointer is going to be highlighting this node in our binary trait representation of this mobile. So again, we see that we don't have a weight on either side because both of these are attached to a submobile, so we can't just magically get the weight. So we're going to have to, again, recursively move down. So now we're going to highlight, this node. So now in this node, both the left and right side weights are right there in front of us, so we can compute this. So in order to be balanced, we have to compute the torque. So the torque would really just be the weight of the left sort of arm multiplied by length. So 1 times 1. This would also be 1 times 1. So they are equal to each other. So far that is balanced. So then the result is you want to return the weight of this mobile. And the weight would actually be 2. Because we have the left weight is 1, right weight is 1, returns 2. So the right side is also not known. So we have to basically compute that weight by calling the function getWeight and highlighting the right side of that that node. So right here we see again, we now at this level, we actually do have a final product because we have the weights right there in front of us. So we compute the torque, which will be 2 times 4. And then here also, I guess I'll say 4 times 2 to be consistent. So they are going to be the same, obviously. So return the sum. So 2 plus 4 is 6. Return 6 up this tree. So now we do have the weight of the left and the right side for this level, because the children returned their weights up this tree. So of course now we have our weight. So now we have 2 multiplied by 3, which will give us 6. Then 1 times 6 will give us 6, so they do match. So we add these up. So we have 2 and 6 return 8 up this tree. And we have to sort of just keep working like that. So you have to multiply, the distances with their weights to compute their torques. If they are same size torques, then just return the sum of their weights. And until eventually at root level, if we have these 2 weights and the torques that are the same, then we have a valid, then we return some type of weight back. So essentially at the very end, the root returns some type of number, and that tells us if this is valid. Now, you have to have a way of being able to determine if the mobile was balanced. So at any level at the top or any level below, there must be some type of value you can return up to the parent that tells the parent that, okay, no, there was some imbalance at some level. So you have to have a way of being able to, how do you denote and how do you actually interpret that? And also, at the very topmost root level, it returns some value back to that validate or validMobile function. You have to sort of know, well, how do I interpret that number? If that number is a certain value, that means it can't be, then it has to be balanced, right? If it returns some specific value, then it has to be unbalanced. So that's sort of more for you to sort of figure out. So of course, in main, all you have to do is create or just declare a mobile type object, read an input file, then call that object dot build tree, and then go ahead and call that object dot validMobile, and returns true, output balanced, it returns false, output not balanced. So that's basically what you have to do in main. And of course, these private functions are going to be called within those public functions. Those public functions are going to be like wrapper functions for these private functions that do all that recursive results. And of course, those public versions are going to interpret the results by recursive functions and be able to determine what happened. So that's basically just sort of the explanation as to how we can, work on assignment 5. Let's go on to the last parts of our of the write-up of the assignment. So I guess, also I have the write-up here that shows some sort of description of the actual functions. And here's the contents of main. I guess there's a typo right there because I have in capital, but I guess it's still understandable what I'm trying to say right there. So I just sort of basically told you what happens in the main. So of course, as always, memory leaks are not good. Try to avoid those, avoid segmentation faults. Of course, document your code as always, and don't have any global variables. So everything has to be done. You gotta pass data to a function either through a parameter, and of course the return of what a function returns some value back to the parent, which will of course have the parent who will interpret that. So everything has to be done at that level, either return something back or pass some value as a parameter into a child function, but no global variables allowed for the assignment. And of course, since it's a templated sort of class, I was able to create a main.cpp, a mobile.cpp, and a mobile.h. I include mobile.h in both main and mobile. I simply compile link them like this. But for this assignment, however, for code grade, it would just do a g++ star.cpp. So it will compile every C++ file you submit. So if you submit one file or multiple files, code grade shouldn't be picky on this one. It should just compile them together just like that. So I just have some input files. So I'm using the same input files I'm using on code grade as I have in this PDF. So they're right there. So of course, that's the assignment. Hope this video did sort of help you out. And as always, take care, guys. Happy coding. Until next time.